Yes, welcome to Easy Gates Gate 22 Easy Solutions once again. Okay, so let us get into the next problem. The next problem is from analog electronics. Given an ideal op-amp circuit, the moment you see the circuit, you know, okay, it's going to be like a filter, okay, a frequency selective network given. The moment you see the capacitor, it is a frequency selective network, okay, active circuit analysis, okay, involving an op-amp. It's an ideal op-amp. So the ideal op-amp shown in figure is what? Okay, that's what given. So it's all about, okay, it's basically an inverting configuration you're all familiar with. Okay, so it's all depends on where you connect your capacitor. If you connect your capacitor in the feedback in parallel to that 20K, it is going to become low pass. Since you put the capacitor in the input side, if you remember that fundamental, immediately you know it is going to be a high pass. Or you can also perceive this way. Okay, so whether it is high pass or low pass, you play with your capacitor. So the capacitor is going to offer what? The impedance or the reactance X equal to 1 by omega. You can play with this, very simple. Okay, omega 0, what is your XC? It is infinity. Omega infinity, what is XC? It is 0. That means it is acting as an open circuit. And here it is acting as a short circuit. Very simple logic. Okay, so that's a not the suggested logic, but still that's okay, acceptable, because instead of going for V naught of S by V in of S, anyway, we are going with that only soon. Okay, but this is the easy intuitive way. Okay, so the capacitor is going to act as an open circuit for DC. That's what it means. Omega equal to 0 is nothing but DC. So infinity is nothing but you can treat this as a very high frequency AC. Okay, so therefore for DC, it is going to act as an open circuit, means so completely the input is not connected to the op-amp circuit, so nothing will come out. So output will be 0. That means it is not passing the low frequency content to the output. So definitely it cannot be a low pass. Low pass means it should be capable of passing even a 0 frequency signal. That's a DC signal. Okay, ideally. Okay, because its frequency response should look like this. Okay, whereas high pass means will look like this. Okay, yes, that's high pass. Fine then. So definitely it is not a low pass, but during high frequency, what happens? Okay, so during low frequency, V naught by Vn is going to become 0. During high frequency, the capacitor is going to offer a short circuit. So what is your V naught? V naught is V naught by Vn. Let me go for. Okay, so here V naught is 0. The gain is going to be 0. So during high frequency, what is going to happen means the capacitor is going to act as a short circuit. The moment you feel this, it's a simple inverting configuration. You can label this as R2. You can label this as what? R1. Then the gain is going to be minus R2 by R1. So it is going to act as an inverting amplifier only during high frequency. That means it's a frequency selective inverting amplifier. That's your high pass. Okay, it is going to offer this inverting gain only during high frequency, beyond the cutoff frequency approximately, we can say. So here itself, the problem is over. So this is the MSQ problem. Here itself, you can conclude. It is already concluded. It is high pass. What is the gain? You need not to go by the transfer function way. I think it is a 1 mark MSQ problem. Okay, so it is high pass already decided. What is the gain? The gain is going to be, so gain means what gain you need to talk about? Modulus of V naught by Vn. So modulus of V naught by, that's how you're going to get the plot. The plot is going to be modulus of V naught by, already you decided it's going to be a high pass. So it's modulus of V naught by Vn. What is the maximum gain? High frequency gain. The high frequency gain, omega 10 to infinity. The gain is going to be 2. Therefore, we can conclude from this itself, it is a high pass filter with the gain of 2 is the right choice. The problem is not over there itself. So this is one of the right choices. It's high pass filter with the gain of 2. Okay, that's a infinite frequency gain. Okay, or high frequency gain. Then what about it cutoff frequency? Okay, cutoff frequency depends on this. So for this, you can have a perception. If you want me to prove it straight away, I can go with this is the high pass, one responsible for the frequency selection. So it's 1 by R1C will be the cutoff frequency. So R1 is given 10K, C is given exact values. Okay, probably this value is exactly matching with the given gate problem as well in gate 22. Yes, R and C product will be equal to R1C will be, so 0.1 into 10 will be 1, and micro and kilo will become milli. So 1 by R1C is going to become, so let me take it. So it's going to be R1 is 10 power 4 and C is going to be 10 power minus 7. So the cutoff frequency is going to be 10 power 3 radian per second. The cutoff frequency will be 10 power minus 3. So 10 power 3 radian per second. So the cutoff frequency is this. Okay, so I didn't remember exactly whether it is given as a f3 decibel or simply the cutoff frequency or corner frequency. But anyway, the data given as 10 power 3 radian per second. It means corner frequency of 3 dB or cutoff frequency, it means same. So only two options given, 10 by 3 or 1 by 10 by 3. Okay, so therefore 10 by 3 is the correct answer. So therefore the two options for this MSQ are correct options are it's high pass filter with a gain of 2 and its cutoff frequency is 10 power 3 radian per second. If you want to go by the formal way, then you have to take this as Z1 of S. Then you have to take this as Z2 of S. Then you have to play. Then you will end up with, so this is taken as Z1 of S. I'm calling it as R1 and call this as 1 by SC. This is Z1 of S. What is that? R1 plus 1 by SC. And this is Z2, that is equal to R2. So then what is V0 of S by Vin of S? Since it's a overall inverting configuration, so V0 of S by Vin of S, you can write it as minus Z2 of S by Z1 of S. That is equal to minus of, what is Z2? It's R2 divided by, what is Z1? It's R1 plus 1 by S into C. Nothing but minus of, it's R2 by R1 divided by 1 plus 1 by S into R1 into C. Okay, so then we are looking for the magnitude only. Even let me go for the normal thing. So then V0 by V in, I can take it as minus R2 by R1 into 1 by 1 plus omega of C by S. That resembles something like K by 1 plus omega of C by S. That's your high pass model, first order high pass model. So what is your K? Minus R2 by R1. Okay, but when you go for modulus of V0 by V in, modulus of V0 by V in will become modulus of K at omega equal to infinity. So that is going to become R2 by R1. With this also, you will get the answer as 2 only. Okay, and the cutoff frequency clearly known from here. Omega C is equal to 1 by R1 into C. Still, you will conclude this is 10 power 3 radian per second. So in any route, it is very simple, but you'll be very confident in the fundamental route. This is the fundamental route. Okay, but instantly you have to connect. You might have already played with this so many times. Okay, during your practice. Very simple. There are two configurations using inverting. One is a simple active high pass. Another one is simple active low pass. This is belong to the active high first order. This is the first order active high pass filter. If you remember straight away, you have the answer. Okay. Yes. So the gain is 2 and cutoff frequency is 10 power 3 radian per second. Okay. Yes. That's a very simple, interesting problem from analog electronics. That's the reason, again, I am saying ECE 22 paper is easier than ECE 2021. Okay. So thanks for watching. Do subscribe our channel. We'll meet with one more problem soon.